Hey everybody, how you doing? I'm going to show you how to do the elevator problem here. This is a really common problem in physics. It will probably show up on your exam, and it is a great example of a problem that seems difficult, but if you attach it or approach it really systematically by first drawing your free body diagram, getting F net from that, and then connecting it to Newton's second law, you'll see that these problems are actually really simple. And this will tie into what some of the other later videos will talk about. So the first thing you need to know is the words apparent weight, scale reading, normal force all mean the same thing. A lot of times in these problems, a person will be standing on a scale in the elevator, and whatever the reading on that scale is, that's the scale reading. That it means the same thing as the apparent weight and the normal force. So your real weight, your mass times gravity, never changes, but your apparent weight can change. If you jump on a scale, the scale reading will change. Okay, so that scale reading is the normal force, your apparent weight. So the first example is a stationary elevator, V equals 0. We are going to draw our free body diagram, only two forces, normal force up, weight going down, and you're going to see that this same free body diagram is going to be used in every situation. So F net from our free body diagram, N positive because it's going up, W minus because it's going down, and we also have F net is equal to ma from Newton's second law. In this case, we're actually going to be applying Newton's first law, which is when acceleration is equal to 0, which is going to tell you that net force is equal to 0. So if both of these are equal to net force, we set them equal to each other. And this is the key thing most people miss when they're doing these problems. They can draw their free body diagram or they can apply Newton's second law, but it's connecting the two that is the main part of almost every free body diagram problem. So what this equation tells us is that N is equal to W. The normal force is equal to the weight, or M times G. Okay, ignore this part right here. So what we're going to see is if we're moving up at 10 meters per second, a lot of people get this problem wrong. They think it's going to change your apparent weight. But what you see when you work at it systematically is that the free body diagram is the same. So going back to our previous problem, we're going to have the same exact net force from our free body diagram, same exact application of Newton's second law, where acceleration is 0. So N is still going to be equal to W. We're going to get the same answer. And we're going to see the same exact thing would happen if we had a velocity of 10 down. Okay, so 0 acceleration, you're always going to have the same apparent weight. Your apparent weight is only going to change when you're accelerating. So if we accelerate up, you might have an intuitive understanding that your apparent weight increases. You feel heavier when you accelerate up. We see this through the application of the free body diagram to Newton's second law. But again, I want you to notice, even when you're accelerating, the free body diagram is exactly the same. The only thing that changes here is now we have a non-zero acceleration. So now instead of the net force being equal to 0, it's equal to m times a. So if I tell you this is a 5 kilogram person, that means his weight is 50, and we can plug this in to find the normal force. Okay, so his weight is 50 plus the additional force to accelerate the person upwards against gravity. So the normal force is going to have to be 60. So you see your apparent weight 60 is larger than your actual weight when you were accelerating upwards. Okay, so the last case here is accelerating down. And what I want you to notice again, same exact free body diagram, really simple. Net force is equal to N minus W. We apply Newton's second law. The only thing that's different this time is that if I tell you mass is equal to 5, my weight is still 50, but now my acceleration is -2, it's going down. Okay, so this is going to reduce my apparent weight now. When you were accelerating down, you are going to reduce your apparent weight. And the most important conclusion about this going forward is that if you were in free fall, so if the elevator is accelerating down at -9.8, or -10, just whatever you're considering G to be, then the normal force is going to go to 0. And the way you can see this is by looking at the general solution to any elevator problem. You need to know how to derive it, but once you know how to do this, this is actually a little bit intuitive. So if you look at every single answer here, what we've ended up with is weight plus ma. Okay, mg plus ma for the normal force. Even going back to the first problem, I told you normal force was equal to weight, which was mg, but this is really the same equation here, N equals mg plus ma, only in this case, the acceleration was 0. Okay, this is the case we're used to when you're standing on the ground, the normal force is equal to weight, as long as you're not accelerating. Okay, so we have a general solution for any type of elevator problem, whether it's accelerating up or down. What I want you to notice is velocity doesn't appear in this equation. It doesn't affect it. Only acceleration does. If acceleration is positive, it's going to make the normal force greater than the weight. If acceleration is negative, it's going to make the normal force less than the weight. And you get the interesting fact here that if the acceleration is equal to gravity but negative, then these are going to give you a perfect cancellation. And I just realized you guys couldn't see the last minute there. So this is the general equation. What you see is that if the acceleration is equal to negative 10, so you're in free fall, then what we have is the normal force is equal to 0. And this makes sense because if you're in free fall in an elevator, your feet lift off the ground, and the normal force therefore must be 0. Okay, thanks guys.